Hello everyone, my name is José Ferreira and I'm a master's student at the Faculty of Sciences of the University of Lisbon and at the Institute of Astrophysics and Space Sciences. And today I'm here to talk to you about forecasting FFQ cosmology with the ΛCDM background using standard sirens, which has been developed with José Mimoso, Nelson Nunes and Tiago Barreiro and has been recently published at Physical Review D. Okay, so here's the outline for the presentation. Let's start by introducing the cosmological model that we have considered. First, the two recent theoretical developments will be considering a model of symmetric teleparallel gravity, where gravity is ascribed to a flat, torsion-free, and metric spacetime. Then we consider a flat, homogeneous and isotropic universe, which is given by the FLRW metric. One can show, using the modified First-Friedmann equation, that the most general function that recovers a ΛCDM background is as follows. Knowing that f of q equals to q, we obtain the symmetric teleparallel equivalent of general relativity, that is a metric theory, which is equivalent to GR. We can see that this model is quite simple, as it only has one additional free parameter, m, which falls back to GR if set to 0. It has also been shown to give promising results in previous analysis, such as the relief in the sigma 8 tension. As such, this is the model that we have considered throughout this work. Additionally, we consider a universe which is composed of ordinary and dark matter, as well as dark energy, an galactic radiation, which is fine considering that we're studying standard sirens, and using conservation laws we can express dark energy as a function of ordinary and dark matter, which results in the following Hubble function, which is the same as for ΛCDM as intended. Now if the background is the same, what changes? The introduction of the function f of q in the action gives rise to an effective gravitational constant, which is generically represented by the following expression. This effective gravitational constant introduces a modification in the luminosity distance of gravitational waves, which is expressed generically as follows, where dl of z is the standard luminosity distance in ΛCDM. For our specific model, the luminosity distance for gravitational waves is the following, where m is taken to be in the units of 1 over h0, and e of z is the Hubble function without the Hubble constant. This difference between luminosity distance for gravitational waves and standard luminosity distance in ΛCDM will be the key in telling our model from ΛCDM apart. So now that we know the consequences for our model, let's introduce the datasets we'll be using, which are standard sirens and type 1a supernova. Since there's only been one standard siren event so far, we must create standard siren mock catalogs. Here I will outline the procedure we employ to generate such catalogs. We start by having the theoretical probability distribution function of standard sirens events as a function of the redshift. We then sample this distribution to obtain a redshift for our event. Let's represent this schematically by saying that we obtain the point marked in red. We then generate the corresponding luminosity distance for that redshift using a reference cosmology, which in our case we took it to be ΛCDM. Then we take the expected error distribution as a function of redshift. For the event that we sampled before, we compute its corresponding expected error and consider it to be the 1 sigma region around the computed value for the luminosity distance. Then, to obtain a more realistic catalog, since most likely values aren't usually on top of the expected value, we generate a new value for the luminosity distance using a Gaussian distribution, which is centered in the theoretical luminosity distance, represented by the red dot, and with a standard deviation equal to the error in blue. We then repeat this process the number of times equal to the number of events we expect to observe for each observatory. To simplify this process, we have created a tool, which is called GW Catalog, which automates this procedure. It is written in Python and as such can be used as a Python package or as a terminal utility. It is also easy to install, it's available on pip, it's easy to use, to extend and to modify if, for example, you wish to update any of the underlying distributions or add other observatories. Now, for which observatories will we perform our forecast? Let's meet our contestants. We have LIGO, LISA, and the Einstein telescope, which I imagine that you're all most familiar with. So besides standard sirens, we'll also be using type 1a supernova. That is because if you look at the luminosity distance function for gravitational waves, E of z implicitly depends on omega matter, meaning that there's a degeneracy between m and omega matter. To avoid problems in our sampler, we'll be using type 1a supernova from the Pantheon sample to fix the value of omega matter. Okay, so now that we have our model and our datasets, let me briefly discuss how we're joining the two together. Because we're talking about catalogs and probability distribution functions, we must provide statistical confidence in our results. To do so, we generated 15 different catalogs for LISA, each with 15 events, and picked the best, median, and worst catalogs. For us to say what the best, median, and worst catalog is, we rated them based on how small the 1 sigma region for our parameter m was. For the Einstein telescope, we generated 5 different catalogs, each with 1000 events, which all showed to be similar, so we only considered one catalog. For LIGO, we generated 15 catalogs, each with 50 events. However, it was unable to set proper forecasts on our model, so we considered the best, median, and worst LIGO catalogs based on how well it would complement the worst LISA catalog. Okay, very briefly, we used a Gaussian likelihood for the luminosity distance of gravitational waves, whereas for type 1a supernova we have performed some marginalizations such that it only fixes the value of omega matter. And for our sampler, we have used STAN, which is a sampler written in C++ that can be used in several programming languages or directly in the terminal, which implements the no U-turn sampler, a variant of the Hamiltonian Monte Carlo method, of which we have used the following parameters for each run. Now let's take a look at the results that we have obtained in our work. First, the forecast set by LISA. We can see the 3 representative catalogs on the left and the corresponding forecasts on the right, where the dashed lines represent the theoretical values used to generate these catalogs, that is, ΛCDM. As you can see that there's quite a big difference between the worst catalog, which is in orange, and the median catalog, which is in bluish. By contrast, the median and best catalog, which is in pink, are very similar to each other. If you analyze this in due time, you can actually see a pattern. The best LISA catalog is the one which features more low redshift observations, while the worst LISA catalog is mostly made up of high redshift observations, and the median catalog is somewhere in between. This makes us believe that there's an optimal region to constrain this model, which is located at low redshifts. It is also important to note that out of the 15 different catalogs that we have generated, only 3 showed forecasts as bad as the worst LISA catalog, so we expect that such a scenario shouldn't be very likely. For the Einstein telescope, it has 1000 events, which is enough to closely match the underlying statistical distribution, which is the reason why we only needed to consider one Einstein telescope catalog. If we take the best LISA catalog and the single Einstein telescope catalog and place them side by side, we can see that the results set by the Einstein telescope are better than the ones set by LISA. This is interesting because, as you can see on the left, LISA has a maximum redshift range which is 3 times bigger than that of the Einstein telescope, meaning that studying high redshift events is not a requirement to constrain this model. Granted, the number of events measured by the Einstein telescope is much larger than the ones measured by LISA. Yet, even with only 15 events, LISA is able to compete, giving only slightly worse constraints when compared to 1000 Einstein telescope events. LIGO, as I said before, is not able to forecast this model by itself, so we had to add the worst LISA catalogs to the mixture. Here we can see the impact of the worst, median, and best LIGO catalogs have on the worst LISA catalog. We can see that there's quite a bit of improvement. This means that if in the future we are unlucky enough to obtain a bad LISA catalog, we can rely on data from LIGO to improve those results and approximate its constraining power to the one set by a median LISA catalog. To understand why LIGO isn't able to provide the constraints by itself, we have zoomed in the low redshift regime and compared the best LISA catalog with the best LIGO catalog, as well as the single Einstein telescope catalog. You can see on the left that the error bars from LIGO, which is in blue, are massive when compared to the Einstein telescope, which is in pink, where the error bars are just barely visible, or in LISA, which is in orange, where the error bars aren't visible at all at this scale. This is the reason why LIGO alone isn't able to forecast our model. The significantly small error bars that LISA has at this redshift can explain why 15 LISA events can actually provide similar constraints when compared to 1000 Einstein telescope events, assuming that we are lucky enough that they land on the right place, of course. Hence, the major differences between the LISA catalogs we have generated. When we add each of the LISA catalogs with the single Einstein telescope catalog, we can see that only for the best LISA catalog there are visible yet small improvements. Unsurprisingly, when one adds LIGO and the Einstein telescope together, there is essentially no improvement at all. Okay, so let's wrap up this presentation with a few closing thoughts. So, the Einstein telescope showed to perform slightly better than LISA. LISA showed to perform better than LIGO. LIGO alone would not be able to constrain this model due to its high error bars. We obtained different catalogs for LISA and LIGO, but not for the Einstein telescope. This is due to the number difference between events. And if we obtain a bad LISA catalog, we can use LIGO as a complement and obtain better constraints. We also show that low redshift events are ideal for LISA to constrain this model. I should reinforce that the machinery that we have developed here is also flexible enough to forecast different cosmological models, something which we are developing at the moment. Okay, so thank you for listening, and I hope you enjoyed the presentation.